This time, I'm going to talk about tracking Ornstein-Uhlenbeck process in Python. In this model, we will use Kalman filter. The Kalman filter is an algorithm that provides estimates of some unknown variables giving a series of measurements over time, even when those measurements contain noise or other inaccuracies. The Kalman filter aims to estimate the current state of a system based on noisy measurements. The Kalman filter works in two steps. Step 1, it predicts the future state of the system using a model. Step 2, it then updates this prediction by incorporating new measurements, adjusting the state estimate and its uncertainty. The Kalman filter assumes that the noise in both the process and the measures is Gaussian, which allows it to compute optimal estimates. The Kalman smoother is an extension of the Kalman filter. While the Kalman filter is used to estimate the hidden states of a process given noisy observations, the Kalman smoother provides a way to refine these state estimates by considering future as well as past observations. So, for Kalman filter, it is forward pass. The Kalman filter operates in two steps, like I just mentioned, prediction and update. And Kalman smoother works in this backward pathway. The Kalman smoother then takes the estimates from the forward path and refines them by running a backward path. It considers information from future observations to adjust the estimates of earlier states, reducing the estimation error. This is done using the smoother gain, which combines the Kalman filter's estimate with the backward-looking adjustment. Now let's talk about process noise versus measurement noise. Process noise represents the uncertainty or randomness in the evolution of the true state of a system over time. It arises from inherent variability in the system dynamics, such as unmodeled effects, external disturbances, or random fluctuation in the process itself. For example, in a weather prediction model, process noise could represent unexpected changes in weather patterns that aren't captured by the model. Process noise affects the accuracy of the state predictions made by a model. In the same time, measurement noise represents the uncertainty or errors in the observations or measurements of the system's state. It comes from inaccuracy in sensors, data collection instruments, or any external factors that affect the quality of the measurements. For example, in the same above weather prediction model, measurement noise could be due to sensor errors when recording temperature or wind speed. Measurement noise affects the reliability of the observed data used to update the model's state estimates. In this model, we have following those steps. Now, let's compare with the Python source code to go through all those steps. This is the Python program I used in this model. First, we'll do some imports and initialization. And then we will initialize parameters and time vector. And then we'll set up Vasicek model parameters here. Then we'll run simulation for the OU process over time using the Vasicek model. And after that, we will perform the OLS regression to estimate the parameters kappa, theta, and sigma from the simulated data. And after that, we will run simulation of Ornstein-Uhlenbeck path. And then we will implement the Kalman filter algorithm to estimate the state of the OU process for noisy observations. And then we will prepare training and testing datasets from the noisy observation. Then we will estimate the parameters alpha, beta, var, eta. This is for the process noise, and var, epsilon. This is for the measurement noise, by maximizing the likelihood using the Kalman filter. And after that, we will implement a Kalman smoother for better state estimation by considering both past and future observations. If you take a look at the source code of this Kalman smoother, you can see when we calculate the state on step K, we use the result from K plus 1. That's why we're saying the Kalman smoother considering both past and future observations. And then we will visualize the true process, noisy measurements, Kalman filter estimates, and smoother estimates. And here we will refine parameter estimates using the Kalman smoother until convergence. Lastly, we will compare the estimated parameters from the Kalman filter and smoother with the true parameters. Now, let's run our model. You can see theta, which is long-term mean, we set 0.5, and OLS theta is 0.507. and kappa, mean reversion coefficient, we set to 3. And OLS kappa is 2.566. And sigma, volatility coefficient, we set 0.5. And OLS sigma is 0.4972. It's very close to 0.5. You can see this is oil process plus some noise. This red line is long-term mean. You set it here, theta 0.5. And this true process is in the center. Because we add some noise, so the process will look something like this. And over time, the process will converge to this long-term mean. And error in estimation of alpha is 33.1%. This is pretty big. And error in estimation of beta is 0.01%. This is small. And error in estimation of var eta is 8.89%. Error in estimation of var epsilon is 0.61%. And if we check this state estimation of the oil process, you can see again this red line is long-term mean, and this is process plus noise. And you can see the smooth state estimate is this line. This is a little bit hard to see. Then we can enlarge only this part. So we zoom in like this. This is 2 to 2.14. So if we zoom in this part, you can see long-term mean here, and smooth state estimate is this one. And then if we compare the estimated alpha against real alpha, you can see the estimated alpha is 0.00044 and real alpha is 0.00032. And for the beta, it's very close. It's both like 0.999, 0.999. And for the var of eta, this is kind of close because this is small. It's 5.8. This is 6.2 about. And for the var of epsilon, this is very close. Both are 0.01. I will upload this Python code to my GitHub. You can download it and modify all those parameters. Run it by yourself. This is how I can track Ornstein-Uhlenbeck process in Python. Please provide your comments, like, and subscribe to my YouTube channel. Thank you for watching.